Thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having John Martyn, who will tell us about halving the cost of quantum algorithms with randomization. So John is a PhD student at MIT. His advisor is Isaac Chuang. In his research, he's interested in quantum information and computational physics with a focus on quantum and classical algorithms. He got his bachelor's from the University of Maryland, and he worked as a student researcher at Caltech and at Google X. I think now it's called X Development or something like that. Yes. So yeah, John, the floor is yours.
Awesome. Yeah, good morning, good evening, good night, whichever time it might be. I'm very happy to talk to you all today, mainly in that I'm very excited by many things in algorithms, both in the quantum side and the classical side, and it seems like many people in the audience here are also interested in algorithms, and so I'm happy to speak on that and cater to those desires. And so what I want to talk about today is this recent work that I put out with Patrick Rao at IBM. And essentially what I'll show you today is a way in which we can take a deterministic quantum algorithm and then strategically inject randomization into it such that we cut the cost of that algorithm in half. So as is kind of hinted at in the title, we have the cost of the quantum algorithms with randomization. And so for instance, you could imagine if you have some quantum algorithm that needs to take, say, like 10 minutes to run, you now randomize over this and it takes 5 minutes to run just by adding in randomization and not really requiring any additional like quantum overhead or anything like that. So I want to walk you all through that. So let me go ahead here and get started. Also, can you all see my mouse if I move it around here? You can? Okay, cool. So as an overview, in recent years, quantum information has really benefited from the study of randomization, right? Like we have these new methods in randomized measurements, in randomized benchmarking, and also new randomized quantum simulation algorithms. And they've like really taken the field by storm. There's lots of cool stuff being studied there. And so what we set out to do in our work is to continue this campaign, but focus on quantum algorithms. And specifically, we want to focus on quantum algorithms through the lens of something known as quantum signal processing, which is abbreviated by QSP, and I will use that phrase many times. And essentially what QSP is, and I'll go into it in more detail later, is a framework for developing quantum algorithms. And it's a way in which you can sort of tie together all quantum algorithms into this universal framework. And so what we do in our work is we develop something known as stochastic quantum signal processing as a randomized extension of QSP. So QSP itself is deterministic, and stochastic QSP is a randomized version of that. And as we'll show, we can use stochastic QSP to design and randomized quantum algorithms that have half the cost of their corresponding deterministic counterpart. And so because QSP, like I mentioned earlier, is this universal framework for quantum algorithms, this halves the cost of a very broad class of quantum algorithms, all through this framework. And the overall takeaway that I want to emphasize is that randomness, that is classical randomness, just, rolling a dice, is a very powerful resource for quantum algorithms and can reduce the cost of those. And then I think there's a lot of like interesting work to be done going forward in this direction. So as a roadmap for this talk, I'll first talk about the two ingredients that underlie stochastic quantum signal processing. First of which is quantum signal processing itself, which, like I mentioned earlier, is this framework for designing quantum algorithms. And then the second ingredient is something known as randomized compiling, which is a tool from sort of like this quantum protocols area where you can sort of suppress errors with classical randomization. And then I'll put these two ingredients together into our main dish, which is stochastic QSP, which, like I mentioned earlier, is a way in which you can design randomized quantum algorithms with reduced costs. And it's essentially a merger of QSP with randomized compiling, as we'll see. So that's the walkthrough. So without any further ado, we can just get ahead and go on into the first ingredient, which is quantum signal processing. And to keep this as simple as possible, what QSP is a methodology for systematically transforming an operator, like a linear operator, by a polynomial. And so what I mean by this is that we begin with some linear operator, which I've called A, and this could be like a Hamiltonian or a matrix that you want to invert, but some like linear operator, i.e. a matrix. And we begin with an operation that encodes this matrix itself in a block of a larger unitary matrix. And QSP allows us to take this object here and transform it to another object that encodes a polynomial transformation of that operator. So P of A. Where by a polynomial transformation, I mean one that acts on either the eigenvalues or singular values of the matrix. And to be concrete, this is realized as a product of non-commutative SU2 rotations. So if you intersperse like a Z rotation and an X rotation, what you get out of this is an operator that can encode some polynomial. And importantly, in QSP, they intersperse this object here that encodes our operator of interest with a parametrized Z rotation, so RZ through some phase phi, where each one of these phases in this interspersed product can be different. And as it turns out, the polynomial that you get out of this is parameterized by these phases. So as we tune these phases, we get different polynomials. And by manipulating these phases, we can in principle generate a nearly arbitrary polynomial up to some conditions, primarily that the polynomial needs to be bounded in magnitude by 1. And this is because the polynomial is a block of this unitary matrix, and because the unitary matrix has an operator norm upper bounded by 1, this also has to be upper bounded by 1. So if you can find any polynomial that fits this constraint, you can generate it with QSP, okay? And also, again, if anyone has any questions about these details, feel free to stop me, but the big takeaway should just be that we go from an operator to a polynomial of that operator. And then lastly, the important part is the cost of QSP, and the cost of realizing a degree D polynomial is D queries to the operator A itself. And this sort of makes intuitive sense because if we want to generate a degree D polynomial, then we need to construct at least A to the power of D, which requires a product of D instances of A itself. And so as a result, for any degree D polynomial, we need D instances of A, and the corresponding cost is going to be O of D, as is the runtime. Okay. So that's a rough overview of QSP and how it works. And what's really crucial here and kind of very surprising and really cool is that QSP unifies quantum algorithms in the sense that nearly all the algorithms that we know and work with today can be derived through QSP itself. And I'll show a couple examples of this. And the key insight here is that you can reduce a problem, say some quantum problem that you want to solve, to a classical function approximation function, or sorry, to a classical function approximation problem, which is a very well understood field. Right? We have these books and texts that show how we can approximate continuous functions with polynomials, and we can do this very well. And so by reducing your problem to this classical problem and solving that classical problem and porting that back to the quantum space, you can construct a quantum algorithm that solves your problem of interest. And that's the workflow. So like I mentioned earlier, we're really boiling down problems to polynomial approximations to functions. And as an example of this, one can consider Hamiltonian simulation, in which case we want to time evolve a quantum state. That is, we want to multiply a quantum state by this time evolution operation, which is e to the minus iht. And so the way to solve this with QSP is to construct a polynomial approximation to e to the minus iht, where now our operator of interest is the Hamiltonian. And so if we can determine some polynomial that's a good approximation to this, we can implement that in QSP and then perform Hamiltonian simulation. And how this is achieved is by noting that e to the minus iht breaks into cosine and sine. And both cosine and sine have well-behaved Taylor series and Chebyshev series. And so as a result, one can construct a polynomial of degree D that approximates this e to the minus iht function to within some error epsilon. And it's known that the scaling of this is D equals to O of t plus log 1 over epsilon. So as time increases, the complexity does as well. And as the error decreases, the complexity grows as well, but logarithmically in the inverse error. And then another similar example is thermal state preparation, in which case we want to prepare the thermal state, that is e to the minus beta h. And very similarly, in this case, what we can do is we can construct a polynomial that approximates the decaying exponential, so e to the minus beta h. And the degree of this can be shown to scale as O of square root of beta times log 1 over epsilon. And so essentially, as we go to lower temperature, that is larger values of beta, we need a larger degree polynomial to approximate this. And similarly, if we want a smaller error, that is a smaller epsilon, we also need a larger degree, okay? And then this trend also applies to a variety of other algorithms like Grover search and phase estimation and linear system solvers and beyond. And it really comes down to determining what function you want to approximate for your problem and finding a polynomial approximation to that function. And one crucial piece to note here is that in both of these examples that I've shown, the degree scales with the error epsilon as d equals O of log 1 over epsilon. And that'll be a very important point. And as I will show on the next slide, this is actually a generic feature of polynomial approximations to smooth functions. That is, if you want to approximate this smooth function, the degree will always scale like log 1 over epsilon. And the reasoning for this actually, is predicated on the Chebyshev polynomials, if you recall these, and I'll review them very briefly. But the order n Chebyshev polynomial is defined as t sub n. It's defined as cosine of n times arc cosine of x. And in essence, it's a degree n polynomial. And in the space -1 to 1, this is what some of the first examples look like. And of course, you might have encountered these in like your quantum mechanics 1 course when you're studying like the hydrogen molecule, or sorry, the hydrogen atom or whatnot. But it's a family of these orthogonal polynomials, and they arise in a lot of cool instances and have a lot of nice properties. And one of the nice properties that we can exploit here is that they're orthogonal, and so we can expand functions in them, sort of like a Fourier series. So some function f of x can be written as a sum over coefficients times the Chebyshev polynomials, where these coefficients are given by this integral, which is again pretty similar to Fourier series. And what's crucial to note here is that for a C infinity function, that is a function that's smooth, that is, it's continuous and infinitely differentiable, these coefficients Cn decay exponentially. Okay, so they decay like some C equals e to the minus O of n. And so therefore, if we truncate this expansion at some degree equal to O of log 1 over epsilon, we can guarantee that our polynomial approximation approximates our function of interest with some error at most epsilon. Okay? And the log 1 over epsilon comes from the fact that this decays exponentially, so if we invert that, we get a log 1 over epsilon. But at the end of the day, that's the crucial point, is that we can construct a polynomial that scales, that has a degree scaling as log 1 over epsilon that gives a good approximation to our function. And so the two key takeaways from this section on QSP, as I'll be moving on to some other things shortly, is that QSP enables us to build polynomial transformations of operators, that is, these P of A for some operator A. And in addition, the degree of these polynomial approximations scales like O of log 1 over epsilon, and so too does the cost of these QSP algorithms. So remember these 2 points because they'll come up again in not the next section, but the following section. So the next ingredient that we will use in constructing stochastic QSP is something known as randomized compiling. And in essence, the idea behind randomized compiling is to randomize over the unitary gates comprising some quantum circuit. So normally when we run a quantum algorithm, we'll run a circuit repeatedly and then measure a state at the end of that algorithm. And an example of this can be, say, Hamiltonian simulation, where you want to simulate a state many times and then measure the output to estimate some expectation value. And you'll run that many times. But what randomized compiling suggests is that within each one of these circuit executions, we run a slightly different circuit, so a slightly different combination of gates. And doing so can actually be very advantageous. So specifically, if you do try to implement this procedure, you're essentially promoting a unitary gate to a channel that's a probabilistic mixture over unitaries. And what I mean by this is that if we evolve under like some unitary channel itself, then our transformation will be some U rho U dagger. But instead, what I'm proposing here is that we're going to randomly compile over these operations. And so we'll really evolve according to a channel lambda of rho that's a sum over some probabilities of uj rho uj dagger. Uj's are some ensemble of unitaries that are, come from some distribution. And what's crucial to note is that we can implement this channel directly by sampling j according to this distribution pj here, and then executing the corresponding unitary uj, right? So we'd execute, say, unitary u1 with some probability p1, or similarly u2 with some probability p2. And what's crucial to note here is that the cost of implementing this is really just classical sampling and then applying the uj's. So it's not really more expensive to realize lambda of rho than it is to realize these uj operations itself. The only overhead is just classical sampling. Now, why do we go through all this pain of considering these probabilistic mixtures of unitaries? And the reason is that these can be shown to suppress errors. And specifically, the performance of randomized compiling is quantified by something known as the mixing lemma, which I will present here. And I'll get a bit mathematical, but the punchline itself is pretty brief. So in the mixing lemma, we can let V be some target unitary that we want to implement. So this could be, say, the time evolution operator itself when we want like a really good approximation to that. But we can't actually implement V exactly, and so instead we have an ensemble of, say, some imperfect unitaries, uj, that approximate V in the operator norm with error at most epsilon. So the norm between uj and v is upper bounded by some epsilon. And as a result, if we evolve under one of these uj's, then that state will deviate from our desired state, that is v rho v dagger, in the one norm error by some O of epsilon. Okay? Now what's crucial is that if we suppose we can also find some associated probability distribution pj, such that the average over all of these uj's provides a better approximation to v, and specifically that now the operator norm between the average over these uj's and v is upper bounded by O of epsilon squared. Okay? Then if that's the case, then it can be shown that the corresponding channel, that is a probabilistic mixture over all of these uj's, provides an approximation to our desired evolved state, that is v rho v dagger, that suffers a one norm error that's now O of epsilon squared. And so by now randomizing over which one of these unitaries we apply in order to implement lambda of rho itself, we can quadratically suppress error from O of epsilon to O of epsilon squared. And so in practice, you could imagine, say, each one of these uj's suffers an error that's like 10%. Then if we quadratically suppress that error, it's now 1%. And the quantum cost is, again, just the cost of implementing these uj's that themselves achieve error O of epsilon. And the sort of classical cost is just doing random sampling, which is in general pretty efficient. Okay, are there any questions about that? Is that mostly clear? We get this quadratic suppression of error by just injecting randomization, but doing so strategically. And really just satisfying this condition here in equation 9. So to provide some intuition on where this sort of quadratic suppression comes from, the way I like to see this is that randomized compiling achieves this performance by randomizing over the errors suffered by each one of these unitaries. And so if we consider n fixed errors that act on some state or some unitary, these errors can act constructively to some O of n. However, if we have n random errors, that is, these errors have varying sign or phase or are essentially incoherent, then they more or less perform a random walk. And if you remember from statistical mechanics, the standard deviation of a random walk after n steps scales as O of square root of n. And so by randomizing over these errors, we can effectively quadratically suppress the error. Okay? So we get this smaller overall error by quadratic factor. Now, in practice, randomized compiling can be seen as a form of error mitigation, and then it can be used to suppress the errors suffered by like some imperfect unitaries or imperfect gates. But what I want to pitch to you all today is that randomized compiling can also be used to suppress algorithmic errors. That is, errors in the actual algorithm itself, say something like Trotter error, that will always be present even if we have perfect gates. And so, sort of through this lens, what I'm trying to pitch to you all today is that this is a form of like algorithmic level error mitigation, and that we're suppressing the error of the algorithm itself and not necessarily focusing on the error suffered by, say, like some imperfect gates or like noise in our circuit, but really truly at the algorithmic level. And to really hit this home, a nice example that I like to consider is just something simple like Trotterization, where in Trotterization, we have some Hamiltonian that decomposes into a sum of two components, say A plus B, and our target unitary is some time step, some time evolution operation for some time step delta t. And typically in first order Trotterization, what we'll do is we'll approximate this as a product of an evolution under A or B, and you can approximate this as some unitary that's A first and then B, or I guess really B first and then A, or the reverse order. So B and then A. And in both of these cases, the error can be shown to be O of delta t squared, right? Like in Trotterization. In first order Trotterization, things are accurate up to first order, but then in second order, you start to suffer errors. And again, this is the algorithmic level error that's always going to be suffered, even if we have like a perfect quantum computer and we're running this algorithm. And so interestingly, what you can show is that if we select probabilities that are both equal to 1/2, and we sample over U1 and U2 with equal probability, then the average of those unitaries deviates from our desired unitary by some error that's O of delta t cubed. And then as a result, the corresponding channel deviates from our desired channel in the one norm by an error that's O of delta t cubed as well. And so this actually has the performance of second order Trotterization, but at the price of first order Trotterization, because we're really randomizing over two different Trotter steps, but we're getting an error that scales like second order Trotterization. Whereas if we otherwise wanted to implement second-order triarization deterministically, there would be an additional gate that we need to apply. So we reduce the cost by something like from factor of like 3 gates to 2 gates, and we get the same asymptotic performance, but at a cheaper cost, just by doing randomization. Now, what I really want you all to take away from this is that randomized compiling allows us to quadratically suppress errors. And incidentally, this has found a lot of uses in a variety of quantum protocols, like reducing the cost of gate synthesis, and it's also merged with triarization to reduce the cost of time evolution. And what we set out to do in our work is to extend randomized compiling to additional algorithms. And because, like I mentioned earlier, quantum signal processing provides this universal framework for designing quantum algorithms, it seems like a great tool for, porting the benefits of randomization to the quantum algorithms literature would be quantum signal processing. And so that's the direction we'll take going forward. So now is the right time to put these ingredients together and develop stochastic QSP. And our goal here, like I mentioned earlier, is to extend randomized compiling to QSP, and through this, the whole suite of quantum algorithms. So all the algorithms that we can implement with QSP itself. And so just to sort of set our expectations right, according to the mixing lemma and randomized compiling, we suspect that we can quadratically suppress errors, that we can go from epsilon to O of epsilon squared. And then if you recall from the first section where I mentioned that the cost of QSP algorithms scales like O of log 1 over epsilon, this quadratic suppression then corresponds to going from something like degree d to degree d over 2. So the cost is roughly halved. And the reason for this is that if we take, say, like log 1 over epsilon squared, this is 2 log 1 over epsilon. And if you run things through the query complexities, you'll find that factor of 2 comes out front, and you get a factor of 1/2. So it reduces the cost by a factor of 1/2 by virtue of this quadratic suppression of error. So I will walk through this in more detail. So in a lot of these QSP algorithms, what we really want to do is to evolve under some function. That is, we have some state rho, and we want to map this to some state f of a times rho times f of a, where f is some function. Right? This is the function that we want to approximate with a polynomial. And so, for instance, in quantum simulation, this operator a is the Hamiltonian itself, rho is some initial state, and f of a is the time evolution operator, so e to the minus iht. And then similarly, in thermal state preparation, a is again the Hamiltonian, rho is going to be some mixed state, like proportional to the identity, then f of a is going to be like e to the minus beta h, such that the product of these outputs e to the minus beta h in total. And so if we use ordinary deterministic QSP, what we do is we construct a polynomial approximation to f of a itself. And specifically, we choose our polynomial to have some degree d, such that the error it suffers is upper bounded by some epsilon. And then as a result, if we do just go ahead and implement P of A with QSP, then this resulting algorithm will suffer some algorithmic level error that's upper bounded by O of epsilon. Specifically is about 2 epsilon. And what I mean by this is that in QSP, we can evolve according to P of A, rho, P of A dagger, that is evolving under this polynomial approximation. And this deviates from our desired state, F, rho, F dagger, by some O of epsilon amount in the 1 norm. And importantly, the cost of doing this deterministic procedure is going to be d queries to our operator a itself, because this polynomial has degree d. Okay, that's the deterministic setting, and let's now contrast that with the randomized setting. And so what we do in our work is we show how to reduce this cost with stochastic QSP. And specifically what we do is we show you can construct an ensemble of polynomials, that is, this collection of polynomials, pj, as well as a distribution, lowercase pj, that is just some probability distribution, that obeys the following 2 constraints. So first, each one of these pj polynomials approximates f of a to within some error epsilon. And in addition, the average of all of these polynomials, according to this distribution pj, deviates from f of a by some error O of epsilon squared. So the average case does better than the individual case by some quadratic factor. And then as a result, if we consider the probabilistic mixture over all of these polynomials, which we will refer to as the stochastic QSP channel, then according to the mixing lemma, this can quadratically suppress error in that the deviation between lambda of rho, our channel, and our desired state, f rho, f dagger, is upper bounded in the 1 norm by O of epsilon squared. So we effectively quadratically suppressed error by randomizing over this collection of polynomials, which individually, again, are as accurate as the polynomial that we considered in deterministic QSP. Okay, I'm not sure how these can be constructed. So another crucial component to realize is that if we now want to evolve under f of a to some overall error O of epsilon, then the cost of realizing the corresponding stochastic QSP channel is going to be the average degree of all those polynomials in that ensemble. And then we'll be randomly sampling and then implementing the corresponding polynomial. So the average degree is, of course, the average according to this distribution Pj times the degree of the polynomial capital Pj. And as we show in our work, this is equal to d over 2 plus O of 1, where O of 1 is some constant. And the origins from this again are the fact that the degrees of these polynomials scale like O of log 1 over epsilon, and this combined with the fact that we get a quadratic suppression of error contributes this d over 2 term here. And then this O of 1 term here is a term that depends on properties of the function f itself, but is indeed just a constant. And so then what's important to realize is that the ratio of the randomized cost to the corresponding deterministic cost, that is d average over d, approaches 1/2 asymptotically with an error that scales as inverse polynomial in the degree d. And so by virtue of this, we have the cost of the underlying algorithm by using randomization, as was hinted in the title of the work. So that's the overall summary of the result. And what I want to show you now is a construction for where this comes from, and it should hopefully alleviate any confusion and provide an intuitive sort of understanding of where this comes from. So in more mathematical detail, what we do is as follows. We consider the Chebyshev polynomials, which, like I mentioned earlier, is this class of orthogonal polynomials that have really nice properties and are denoted by t sub n. And so we expand our smooth function in the Chebyshev basis, where these coefficients, like I said earlier, decay exponentially with n. And then for the polynomial that one takes in QSP, typically this Chebyshev series is truncated at some degree d, so that's a corresponding deterministic polynomial. And then what we do for our ensemble of polynomials is the following construction, where for each one of these pj's, we take it to be equal to the degree d over 2 truncation. That is, rather than truncating at d, we truncate at d over 2. And then we add to this a randomly sampled higher order term that's in the range d over 2 up to d. So we keep the lower order terms, and we randomly sample one of the higher order terms. And we divide by pj here in order to guarantee that the average over all of these polynomials is equal to the degree d truncation itself. So if you multiply things through and add over all these polynomials, this will just cancel out, and you'll get this this polynomial itself, which is the truncated Chebyshev series. Okay, so again, it's fixed lower order term and randomly sampled higher order term. And the next step is to determine what we want to use for the probability distribution. And what we're able to show is that one can simply imported sample with a probability that's proportional to the weight of the coefficient in the Chebyshev series. So we sample the polynomial capital Pj with a probability that's proportional to the absolute value of the corresponding Chebyshev coefficient. And like I mentioned earlier, these decay exponentially, so this will be some exponential distribution, e to the minus O of j, or upper bounded by that at least. And then as a result, the average degree is going to be dominated by the fixed lower order terms, because the mean of an exponential distribution will concentrate sort of near its origin. And that origin here is d over 2. And so as a result, the average degree will be some d over 2 plus some O of 1 term due to that concentration. And so the following picture summarizes what I mean, in that on the left, on the sort of y-axis here, we have our coefficient Cn, which eventually decay exponentially, but might start at some appreciable value. And in constructing a polynomial, we always include these fixed lower order terms, which I have here in the first half, and then we randomly sample over one of these higher order terms. Okay? And as a result, we're randomly sampling according to some exponential distribution, such that the average is going to concentrate somewhere near d over 2, but shifted by some O of 1 value. But in any event, it'll be d over 2 in the asymptotically large d limit. Okay? So that's sort of like the picture to keep in the back of your mind. And then to sort of illustrate what's really going on here under the hood and sort of give you a picture of how stochastic QSP really works is as follows. So if we want to implement an algorithm through QSP with the accuracy of a degree d polynomial, what we do with standard deterministic QSP is that in each run of our algorithm, that is each shot that we take and then measure the result at the end of the day, each experiment will use a degree d polynomial. That is some circuit of depth d, because the depth of QSP is going through the degree itself. And so we get a picture like this, where each one of these experiments has the same degree, where each one of these blocks is just referring to accessing the operator itself. And then on the other hand, in stochastic QSP, each experiment has a different degree that averages to about d over 2. So it's that d over 2 plus O of 1, where many of these degrees will have degree very close to d over 2, but some of them will be larger. We only need to sample those larger degrees with a small probability, such that on average we still get the same performance as standard QSP, but at a reduced total cost, because each one of these is not nearly as long as this. So that's sort of what's going on under the hood. So each one of these samples runs a slightly different polynomial. And then there's two conceptual points that I want to discuss in that when talking about this, they're kind of concerns that have come up, and I want to make sure that they're alleviated. The first one is, like I mentioned earlier, stochastic QSP is an instance of this sort of framework of algorithmic level error mitigation, in which we're using an error mitigation technique, that is randomized compiling, to suppress the algorithmic level errors, and not the gate or experimental errors. So I haven't assumed anything about the gates or the platform that we're using, such that this framework is still compatible with, say, a noisy quantum computer. It makes no assumption about that noise. And another point is that stochastic QSP is indeed compatible in larger quantum algorithms. And the concern here is that stochastic QSP, as I've presented here, is really an incoherent mixture, right? It's a probabilistic mixture over different unitaries, and it's in itself coherent. However, in our paper, we prove a diamond norm bound between the channel of stochastic QSP and our desired state. That's, again, going to upper bound by some O of epsilon as we desire. And then as a result, one can simply replace some deterministic QSP sequence with a corresponding stochastic QSP channel. And you'll, again, retain the same performance, but at a reduced cost, with the only additional sort of overhead of just doing classical sampling. So wherever one is using QSP, one can replace it with stochastic QSP, and by virtue of that, it's generalizable and compatible in a large class of quantum algorithms. So to really hit this point home, we might as well do some numerics and see how well things actually do in practice. And so as an example of our stochastic QSP framework, we can consider the quintessential problem in quantum information, which is time evolution. In which case, like I mentioned earlier, we want a polynomial that approximates the complex exponential, which requires us to approximate cosine and sine as polynomials. And so if we go ahead and apply stochastic QSP to this and try to, emulate the evolution under some Hamiltonian, then empirically what we find is as shown here, which illustrates how the cost reduction for the function cosine of tx with analogous results for sine tx decays to 1/2 as d increases as intended. So if you remember earlier, we had shown that the ratio of d average to d is going to be 1/2 plus O of 1 over d. And indeed, things decay to 1/2 with an error that scales like 1 over d. And then in addition, the decay rate is different for the different times that you're looking at. So if you look at a larger time, the decay rate will be larger. And this is generally to be expected because we won't really reach this asymptotic scaling until we get to a larger value of time, in which case the approximation to cosine itself starts to get very good and we enter this asymptotic regime, okay? But at the end of the day, for a variety of times, we indeed find that we can have the cost of the algorithm through stochastic QSP, as we theoretically proved. And then as another example, we can consider imaginary time evolution, in which case we want to approximate e to the minus beta h. And like I mentioned earlier, this degree again scales as some O of square root of beta times log 1 over epsilon. And here we observe a similar decay to 1/2 with an error that scales as O of 1 over d, for again the ratio of the randomized cost to the deterministic cost. And interestingly, we found that we can actually get a decay from below 1/2, where again the error from 1/2 still deviates as O of 1 over d, but this originates from the fact that this O of 1 term that I mentioned earlier, that depends on the function of interest, can be negative in some cases. And in that case, you'll just get a decay from beneath, but things are okay because, again, in asymptotic limit, this approaches 1/2 as we expected. And in addition, we also obtained similar results for other algorithms. So for things like ground state preparation, we want a polynomial that approximates a step function such that we can filter out the ground state. And the step function is very well approximated by the error function, which itself is sort of like a step. It's a step near the origin. And in this case, we again find a nice decay of the ratio of the randomized cost to the deterministic cost and approaches 1/2 the asymptotic limit. And then similarly for matrix inversion, in which case we want a polynomial that approximates the inverse function 1/x. Again, here we find that the ratio of these costs decays to 1/2, as we theoretically proved. So overall, these numerics and the theorem that we had earlier shows that through stochastic QSP, we attain this nice cost reduction for a very wide class of quantum algorithms. We just cut that cost by a factor of 1/2 asymptotically. So in summary, what I've shown you all here today is that what we set out to do was sort of extend the notion of randomized compiling, which is again this error mitigation technique to quantum algorithms through quantum signal processing. And we're able to achieve this by developing stochastic QSP, which itself implements a probabilistic mixture over these QSP polynomials that suppresses error or equivalently reduces the cost of the overall algorithm. And because these algorithms have a cost that scales like log 1 over epsilon, this cuts their cost by a factor of 1/2, as I've emphasized earlier. And then before concluding, I want to discuss a bit on sort of the philosophy and like the thinking behind this and going forward. And after discussing with some people, we sort of arrived at the following sort of mentality, which harkens back to this famous quote by Einstein where he says, God does not play dice, in reference to the nature of quantum mechanics, and the fact that he wanted to believe that nature is not random and rather is deterministic. But as we know from various experiments, this isn't true, and quantum is random, and in some sense, God does play dice. And so what I want to pitch to you all today is that in order to better understand nature, we too should play dice. That is, we should develop randomized algorithms. And if we do this strategically, we can obtain a winning hand that is faster algorithms. I think there's a lot of cool work to be done towards this direction. And specifically, I think that the applications of randomization, there's many, and randomized compiling seems to be a broadly applicable tool. And I'll just mention a couple here. Notably, randomized compiling also applies nicely to quantum Monte Carlo algorithms, in which we're also going to be randomly sampling over many states, and we can benefit from adding an additional layer of randomization to each one of these trajectories in a quantum Monte Carlo algorithm. And for reference, these are these classical simulation algorithms that we can run to simulate, say, open quantum systems and quantum chemistry and lattice gauge theory and beyond. And those can benefit from randomized compiling in a similar manner to how quantum algorithms can benefit from randomized compiling, as we've shown here. And then in addition, outside of just physics, there's been a lot of work in the numerical linear algebra world on integrating randomization into their techniques. And because at the end of the day, quantum mechanics is really like linear algebra at its core, I think we could also benefit from adopting a lot of these techniques into our field as well. And then finally, to take another step back, as I've emphasized earlier, stochastic QSP itself is essentially algorithmic level error mitigation, in that we're using these tools from error mitigation to suppress the algorithmic level errors. And I will, of course, mention that randomized compiling is one tool in the toolbox of error mitigation, and there's a lot of other tools like polytwirling and probabilistic error cancellation. And I'm curious, what other of these tools can we use to our benefit in quantum algorithms and perhaps also in classical algorithms for quantum simulation? And so with that said, I want to thank you all for listening. And if you're interested in learning more, feel free to take a look at the paper here.
Thank you very much, John, for very insightful and interesting topic. Yeah, so I guess, yeah, we have plenty of time for questions and for some discussions. So yeah, anyone who has questions, you can feel free to unmute and just ask them now. Maybe I can go first. I have a simple question. So you need, like in this kind of, in order to get this kind of suppression of the noise, of the error, like, so there's a target unitary and then there's an ensemble. I was just wondering, like, so for the problem, for whatever problem you have, it's going to be clear what is the size of the ensemble that you need?
Ah, right. So like how many unitaries are in this ensemble?
Yeah. Yeah.
Yeah, I don't know. I think it will depend on the case. I don't have like a general bound on how many unitaries you can imagine are in this ensemble. But in our case here in stochastic QSP, and I guess I didn't really emphasize it in the talk, but our ensemble is constructed as, yeah, here it is, as again this fixed lower order term plus these randomly sampled higher order terms, and there's only d over 2 of these higher order terms, and so our ensemble is of size d over 2. So it only depends on the degree of the polynomial and doesn't scale like exponentially in that.
Oh, okay, so
but in full generality, I don't have a bound on like what you'd expect that to be.
Right. Okay. Yeah, okay. I should let other people go first.
Okay, thank you for a nice talk. I have a conceptual question. So when you do the randomized compiling, it means that you actually you are using many unitary to replace some target function, some target gate, for example. And so in doing the simulation, does it mean that you run many different simulations and do the average to get the result, or you just sample one and to see how it works? It's just conceptual question. Yeah.
Yeah. So in general, in a quantum algorithm, you'll need to run things many times so you can measure some observable or some quantity of interest at the end of the day. So in something like Hamiltonian simulation, you'll evolve a state many times and then measure an expectation value. But each one of those measurements will either give you like a 1 or a 0. And so if you want to measure like a correlation function or some other operator, you need to average over all of those instances. So at the end of the day, we're already going to be running many different samples. And what I'm saying is, rather than run a deterministic sequence or deterministic operation in each one of those samples, we slightly change the sample, or we slightly change the unitary in each one of those samples. And if we do that slight change according to this prescription here, we can suppress the algorithmic error such that our estimate is going to be a better estimation of the true quantity than if we had we done things deterministically.
I see. Okay, thank you. And a follow-up of the question from Gerald. So for the ensemble you use, does it matter you just fix to some Clifford ensemble or some ensemble, or they make a difference?
Could you specify the question a bit? Like if you were to do
for
what
the
versus...
unitary ensemble you choose, and you choose to be specific some ensemble like Clifford unitary ensemble, for example. If you change, you constrain the ensemble, will they change your result?
If you were to constrain it, how?
The ensemble you choose, the unitary ensemble, you sample.
Yeah. So I mean, like if you were to reduce the number of unitaries that you're sampling over?
Or the type of the unitary.
Yeah, I mean, it will change the output, and what you really want is to satisfy equation 9 here, such that the average case is still O of epsilon squared accurate.
Okay, see.
Right? And so I guess if you do change the size of the ensemble, that's okay, as long as this is still satisfied.
I see.
So the construction we put forth here, there's no guarantee that that's the best ensemble you can do. But in general, you won't expect to do better than an O of epsilon squared error at the end of the day.
I see. Okay, thank you. Very good.
Yep.
Yeah, very nice work. Thank you.
Thank you.
Hi, I have a question. First, thank you for the talk. It's very nice. And so for, say, if I want to do a quantum simulation, so maybe the first thing I have to do is like to choose my unitaries, and then maybe I have to do a expansion to find the PJs. Is that enough, or is there any other trick that I have to be care of?
Yeah. So I mean, at the end of the day, if you want to apply stochastic QSP to some function like Hamiltonian or like e to the minus AHT for Hamiltonian simulation,
Yeah.
what you do is you can, like I mentioned earlier, you can construct things like this. And there's a well-behaved Chebyshev series for the time evolution, so for the complex exponential, which again is used to implement the time evolution operation. And then what you do is you find these polynomials, and then you need to sort of transpile these polynomials to QSP. And the way to do that is to find the corresponding phases that implement that polynomial. So like I mentioned earlier, way back on one of the first slides here, is that QSP itself is parameterized by these phases, which are these rotation angles. And so we know classically the set of polynomials that we want to implement, and there's a classical algorithm that we can run to determine the corresponding phases that implement this polynomial. So to sort of give the overarching workflow, it is we take our function of interest, we determine the ensemble of polynomials according to the Chebyshev expansion of that function, and for each one of those polynomials, we find the corresponding phases here, which, to reiterate, can be done classically and efficiently. And then with all of those phases, we randomly sample over the corresponding quantum circuits, and doing that suppresses the error as I've presented here.
Okay.
Does that make sense?
Yeah. Yeah.
So there's like some classical pre-processing that needs to be done, but once all that is done, then you can just randomly sample and run the quantum algorithm.
I see. Thank you.
I have a question. Sorry, do you mind just explaining why you took the degree to be d on 2 plus some order 1? Like, what if it wasn't? What if you didn't choose d on 2, but something else like 2/3 d or something? How does this change things?
Yeah, this is a good question. I've gotten this before and I've given the talk. So the reason why we chose d over 2 is that in general, you wouldn't expect to do better than d over 2 at the end of the day, because like I mentioned earlier, the error decays exponentially with this degree. And so the degree goes as log 1 over epsilon. And so because we have this quadratic suppression that transfers over this factor of 1/2, and so d over 2 is what you'd expect to achieve. And so if we were to instead do something like, say, d over 3, then so I don't have the condition here. Okay, so, sorry. So suppose we did d over 3. Well, let me see, what's the best way to put this? The best we can do is to quadratically suppress the error, which corresponds to doubling the degree, right? And so if we did instead degree d over 3, and then we did this whole process, and we quadratically suppressed the error that's suffered by an approximation that has roughly degree d over 3, because, mind you, the bulk of the polynomial itself is in this here, and this is just a randomly small term. So if this were instead d over 3, and then we randomize over these things, the error that we would get out of that polynomial would be equivalent to roughly a degree 2d over 3. But we want something that's equivalent to d itself. So that's why we choose d over 2 as that midpoint, such that when we double it, we get something that's as good as degree d. Does that make sense?
Yeah, that's great. I have one more question, but I haven't really thought this through, so I'm not sure how much sense this makes. But have you considered, instead of doing like classical, like stochastic kind of random sampling, doing this coherently, like where you do like a quantum randomness, where you have like a coherent source of randomness? Like, because like in quantum Monte Carlo, you can potentially get speed ups from making the randomness quantum. Is there a potential improvement to your results if you guys consider this?
Yeah, I haven't considered this. I guess, I mean, at the end of the day, all we want is the performance of the average polynomial, and you could develop some coherent way to add these polynomials together. But I guess if you were to do that, then the cost of that circuit would be more expensive than sort of just running the deterministic case itself. Like you sort of need to add together multiple polynomials with like an LCU circuit, which maybe there's some construction that is really efficient, but I guess my gut instinct is that might be more expensive than just doing the deterministic case itself. Whereas what we have here can be implemented on a platform that, if you suppose you already have the ability to do the deterministic QSP sequence itself, then you can just go ahead and make it stochastic and improve the performance. But there might be a way to do this coherently, and perhaps there could be an advantage in some regime.